Today we're going to talk about the Pythagorean Theorem and how it's used. And so in today's note-taking session, when we're done, we want to make sure we understand what the Pythagorean Theorem is and how we can use it to find distances between any 2 points on grid paper or dot paper, or really any 2 points anywhere, which is the purpose of the Pythagorean Theorem. So here I've drawn a right triangle, and this represents a right angle right here in this corner of the right triangle with a square drawn off of each of the 3 sides of the right triangle. Now we need some different definitions. This particular square on this side is called a leg square, and so is this one here. So we have 2 leg squares. The leg squares are off of what we call the legs of the right triangle, and this square is the hypotenuse square, and it is off the hypotenuse side of the right triangle. It's always actually the largest of the 3 squares. So this is the large square, the hypotenuse square, and we have the 2 smaller squares for the legs. The hypotenuse square is the long side. The leg squares are always attached. They're always connected. So these are always connected by the right angle. So when you see that right angle on a right triangle, you know that the 2 sides connected by the right angle are the leg sides of the right triangle, which is very important because they are distinguished that way when you are using the Pythagorean theorem to find different parts. Now if we just look at some of these parts, like this leg length is 4 and this leg length is 6, and right now we don't know exactly what this leg length is, but in just a moment we'll be able to figure that out using the Pythagorean theorem, or at least using the ideas that we'll use in the Pythagorean theorem. So if we find the area of these 3 squares now, this square's area is 16. It's 4 squared, 4 times 4, which is 16. The length is 4, the other length, this direction is 4. There's 4 sets of 4. It's 4 squared is the area of that square. This square's area is 36 because it's 6 by 6, or 6 squared. And so the area of this square is 36. The area of the hypotenuse square we come to find, if we can do it kind of just by actually finding the area. So we're going to do that first, just to be certain. You could use the Pythagorean theorem right now, but before we do that, I want to be sure that it actually works. So if I think of this square and broken up into smaller pieces, and then these triangles here, so this triangle would be base times height, or 4 times 6 would make a rectangle divided by 2. So 24 divided by 2 is 12. So this little triangle here is 12, and they're all the same. Here's this one's 12 and 12 and another 12. So I have the 4 12s, which make 48 plus 4 in the middle. So 48 plus 4 is 52. So the area of this whole square is 52 square units. And so that largest square's area equals 52, which means that the length of the hypotenuse side of the triangle, since this is the hypotenuse square, that's the hypotenuse side right there. That hypotenuse side length has to be the square root of 52, because we know that if the area of the square is found, then the side length is the square root of the area. Just like 4 is the square root of 16 and 6 is the square root of 36, the side length is the square root of the area. So this side length is whatever the square root of 52 is. And since it's not a perfect square number, we just leave it as the square root of 52. We could simplify it, but for now we're just going to leave it as the square root of 52. Now the interesting thing about this is that if you take the areas of the two smaller squares and add them together, so if we have the 16 plus the 36, we actually get the 52. In other words, if we take the area of the leg square plus the area of the other leg square, so in other words, we take the two leg square areas and add them together, we actually get the area of the hypotenuse square. So this is our hypotenuse square area, which can be really helpful at times when we have right triangles, because these two triangles are actually pretty easy to find the area of. This one takes a little more work if we're going to do it the hard way and cut it up into pieces. Or if the Pythagorean theorem always works, we can just simply use these two smaller squares added together to give us the larger hypotenuse square area. And so what that means is that we kind of have a rule now that we can follow. I'm going to write the rule out that we have so far, is that the area of the leg squares added together, so we took those two leg squares and we added their areas together. So the area of the leg squares added together always equals the area of the hypotenuse square. So that hypotenuse square area, so the area of the leg squares added together always equals the area of the hypotenuse square of a right triangle. That's what the Pythagorean theorem basically tells us, is that if we take this area plus this area, the 16 plus the 36, it will give us the area of this hypotenuse or larger square. The two smaller squares areas added together give us the larger square area, which is helpful for finding the area, but it's even more helpful for finding this length, this side of the square. Because when we have found areas of these squares, more often than not, we're finding the area so that we can find how long the sides are. And so what this gives us is not just a way to find the area of this square, but to actually find the length of the hypotenuse side of triangle. So we're going to say this other note is that the length of the hypotenuse is the square root of the area of the hypotenuse square. Which means right here we get the length of the hypotenuse from the area of the hypotenuse square. Since the area is 52, the length has to be the square root of 52. The length is the square root of the area. So the whole point of finding the area is to get the length of that side. It's not an easy side to just look at and know how long it is. These ones are simple, 4 and 6, because you can just count squares. This one you can't just count squares, you actually have to calculate that distance from this point to this point on that right triangle. And so the Pythagorean theorem, the idea of adding these two areas to get this area to give us that length, is a very important theorem in mathematics. So what we're going to do now is just kind of generalize this idea as a theorem, and we can again look at a triangle, a right triangle, and this one I'm not going to focus so much on the actual lengths as I am on as the concept. So I'm going to actually label these different lengths A. So this leg is leg A, this is leg B, and over here we actually have the hypotenuse length C. So we're going to call them A, B, and C now. Whatever length they are. We could actually measure these with the squares, but we're just going to leave it for now and just assume this length was whatever length we have for any right triangle. So we still have a right triangle. There's a right angle there. These are the leg sides, and this is the hypotenuse side. The long side is the hypotenuse. The other two sides are the legs. And so this square here is the leg B square, and its area is B squared, B times B. Whatever length B is times whatever length B is, we have B squared, and this is leg square A, or leg A square. It's the square of leg A, so its area is A squared. And then we have the hypotenuse, which is the C side of the triangle. So this is the hypotenuse C square. And its area then, if this length is C, would have to be C squared. So now we have these three areas, the area of leg A square, the area of leg B square, and the area of hypotenuse C square. And based on what we saw in the previous example, if we take these two areas, so A squared plus B squared, they should add up to whatever C squared is. And this is the actual Pythagorean theorem as it's stated: A squared plus B squared equals C squared. So in other words, the area of the leg squares added together gives us the area of the hypotenuse square. So we know that area for this one is C squared. And so we add those two to get C squared. Now, the real usefulness is finding the length C. Because if we want to know what C is, we're going to take the square root of the area. So we're going to take the square root of C squared. So C is equal to the square root of C squared. This is the length of the hypotenuse, which is what we actually want. And we got it by taking the square root of the area of the hypotenuse square. And this is the real usefulness of the Pythagorean theorem, is to find this length C. So to find length C, if I know A and B, I can find C. The other is true also. If I know any of these two, I can find the other one either by working backwards with subtraction, or eliminating, or isolating the one side and solving the equation for that one side. But however it goes, I really just need two of the three sides to find the other one, and the Pythagorean theorem allows me to do that. So just to make sure that this actually works, let's look at the actual lengths here. If we look at the actual length of A, in this case A would be 4 units, and so the area of that square, A squared, is 4 squared, or 6. And the B side is 1, 2, 3, 4, 5, 6, 7. So B is 7 units long. And so B squared would be 7 squared, or 49. And so if our theorem holds true, A squared plus B squared would be 16 plus 49, or 65, would equal C squared. And so the area of this piece should add up to 65 if we wanted to calculate it, and just to check and make sure we could cut this into pieces here and see how all those pieces fit together. So let's just do that to be certain that it actually adds up to 65. Because if for some reason we're just taking this Pythagorean theorem as true without testing it, making sure it works. So I'm going to take here and see I have 1, 2, 3, 4 by 7, so 28 divided by 2 is 14. So each of these little parts is 14, 14, 14, and 14, and then there's 9 in the middle. So if I put all those together, 14 times 4, and that's 56, plus another 9, gives me a total of 65. So it does add up to the 65, which we expected it to. And so we do have a situation where we take the area of the two smaller squares and they do add up to the larger square, which then gives us what we really want to know is the length of side C. We have C squared, but remember, to find C, we need to take the square root of C squared. So we're taking the square root of 65, which if we actually calculate out on a calculator is about 8.1 units long. Most of the time we will leave it in this form because that's good enough. But if we want to actually calculate it out, and that gives us a sense of a side length of 4 and 7, and this is a little more than 8. And it's the long side. It makes sense that this is the longest of the three. So we have these two that are shorter on the leg side, and the hypotenuse is the long side of the triangle. So it works. And so the idea with the Pythagorean theorem is that hopefully it always works. That would be the idea behind the Pythagorean theorem, is making sure we have something that always works, and that gives us some certainty to be able to use it in different situations. So let's just check it here with one last triangle. And this time I'm not going to draw the squares off the sides. I'm going to assume that the Pythagorean theorem works, and so, because so far it has. And if I just look at these different side lengths, for instance, this side, this leg, this is a leg side, 1, 2, 3, 4, 5, 6, 7, 8, and its length is 8. So if I were to actually draw that leg square, the leg square that's on this side, its area should be 8 squared, or 64 square units, if I were to draw the square. And if I were to draw the square on this side, 1, 2, 3, 4, 5, 6 units long, then it would be, this is my other leg square, so 6 squared. And so now I have what would be a leg square here, and a leg square area here. And that means if the Pythagorean theorem is true, the hypotenuse square area, the area that's on, if I were to draw the square out here, which sometimes that's hard to do and make it accurate and then try to find the area, but if the Pythagorean theorem holds true, then I should be able to take these two smaller areas, 36 plus 64, which gives me 100, and that should be a squared plus b squared equaling c squared. That 100 is c squared. And so if I know c squared is 100, I know that c is the square root of c squared, which is the square root of 100, which is actually 10 units long. And so rather than drawing all those squares and finding all those areas by counting squares, I can use the Pythagorean theorem, which says the area of the two leg squares will add up to the area of the hypotenuse square, and then I can use that area to find this distance. This distance is the square root of 100, or 10 units long. And again, 6, 8, and then the 10 is the long side. It's the longest of the three sides. And once again, the Pythagorean theorem, we believe, which says that the area of the leg squares of a right triangle always add together to equal the area of the hypotenuse square. And by doing this, we can use this to find the distance, really, between any 2 points anywhere. Any 2 points. So if I picked any 2 points anywhere, I could actually make a right triangle and find the distance between those 2 points using the Pythagorean theorem. And that's primarily what we use it for, is finding distances between points. And so hopefully that helps you as you do activities and try to solve problems using the Pythagorean theorem. A lot of people just remember a squared plus b squared equals c squared, but unless you understand how to apply it to find these distances, it will just be a mathematical formula. Hopefully this helps explain how it works and where it comes from.